right. Morning, everyone. We're getting some sun briefly, so that's nice. Hopefully it'll stay for the rest of the class. All right. So there's a couple small things I wanted to kind of clear up or mention from last time, and then we're going to move on to the main topics for this week, being arrays and classes and stuff. Okay, but so first, this is this program that we looked at last time. This is this test program for, I guess this is a test program for project 1011C. And it has some if statements, right? And so we've spent a while talking about how to compile if statements. There's one thing that I kind of messed up, or not exactly messed up, but I forgot about when we did this. And it's something that I think, well, I'll just say what it is. And it doesn't matter so much on project C, but it's going to matter a lot on project, well, maybe it does kind of matter on project C. It doesn't matter much on project B, but it does matter on, anyway, here's the thing. If you remember, the way the return instruction in the VM code works is that it just assumes that there's always a return value to be returned, right? And it copies it somewhere. Okay. In particular, that means when we have a function or method that is void, okay, that means, like, as far as the program is concerned, it's not returning anything. They don't care. However, from the point of view of the virtual machine, every function has to return something. So we have to remember to, like, put just like a 0, or it doesn't even matter what the value is. Might as well be 0 because that's easy. We just have to put some kind of fake return value on the stack. And then conversely, when we call a void function, we have to remember to pop that fake return value off the stack to get rid of it. And I forgot to do that when I was translating this code. So if you'll notice, so 2 places. Number 1, when we call output.println, output.println is void. It doesn't return anything. It just prints something on the screen. So we really should, right after that, pop something. Also, this call output.println, we should also pop there. And then at the very end, when we do the return, we should, I guess I didn't even actually I should have put the word return here, which I forgot. But right before we return, we should push something on the stack and then return. Now, in this specific example, and actually there's some specific tests in project, maybe it's project B, I think, or project C, that work the same way. Notice that the last thing that happens is we call either one of these printints, and then we immediately return. So actually, this one works even if you forget to do this, because these calls to printint will push a fake return value on the stack. We then forget to pop it, and then also forget to push something and return. That fake return value is still there, and so it just works, because when we return, it's like, oh yeah, there's my return value. It's still there from before. But obviously, if you really are forgetting to do it, then it's going to come back to bite you later. You could imagine something that like optimizes for this, and it's like, oh, if I notice that the last thing I'm doing is calling a void function and then returning from a void function, I don't have to pop and then push again. I'll just leave it there. But that would be kind of an optimization that. So, several of you turned in. Maybe it was project B, I think, where basically this happened, and I assume I didn't look carefully at your code to tell the difference between whether you forgot or whether you were actually trying to be really clever and optimizing this. But in general in those cases I gave credit, but I wrote some comments saying, hey, in case you forgot, remember you have to do this. So the way we would fix this, right? We just have to say something like, here we have to say pop and we have to pop it to somewhere. But we might as well say like, you know, temp, I don't know, temp 3. Who cares? I think temp is big. How big is temp?
I
Maybe it's
think
only, yeah, it's only 3 things, so 3 is not valid. We could say 2.
I think they use
It's
like
5?
temp 0 or local 0 or something in the.
You don't want to say local 0 because that would clobber whatever variable you actually have in local 0.
Then
Yeah.
you use temp 0.
You can use temp 0. I am going to, so today when we're talking about arrays, we're going to use temp 0 for something. I mean, it doesn't matter, as long as you just want to make sure that if you are using temp for something, that you don't like put something else there when you're actually in the middle of using it. So I'm just going to say temp 2, it's like probably we're not going to use that, it really is truly temporary. It'd be cool if you could say something like, you know, pop constant 5, and it would just ignore that and be like, well, you can't possibly change the number 5, so I'm just going to assume you mean you want to throw this away or something. Because like there's no particular reason that there couldn't be a VM instruction that just pops from the stack and doesn't store it anywhere. The VM just doesn't provide that. So we can do that here. We can pop here, and then at the end we can say, you know, push constant 0 return. So that's kind of how we would do that. And yeah, in some of the tests, I think for project B, you know, ideally the VM code ends up looking like it says, you know, pop temp 0 and then push constant 0 right after it, but it's fine. So how do you know whether you need to, for example, you know, do this pop right after you do a call, and whether you need to do push constant 0 before you return? How can you tell whether you need to do that?
Oh, I know, the push constant 0 is if our function is void.
Right, so if the function that we're currently compiling is void, then we have to do this push constant 0. How do you know if the function you're currently compiling is void?
We store it.
Yeah, you store it in a variable, right. I mean, just when you start reading the function, you know, you're reading this, and maybe when you started you just ignored this return type, but here's something that you actually need it for. You at least need to know if it's void or not. And so you could maybe just have a Boolean. It's like, is it void or not? And if it's void, then I need to put that push constant 0. I don't think, I actually think that's, because, Jack, because we're not doing any type checking, and every value is stored in 16 bits, I don't think we actually are ever going to need anything other than is the return type void or not. In a more complicated language, in a real language, you might need that because maybe, you know, depending on how big that value is, maybe you need to do something different, how you're going to store it. I don't know, but basically that's all we care about. How do you know? This is a slightly trickier question. When you well, it's both trickier and not, I guess. How do you know if you should do this? Like when you call something, if you should like throw away the return value or not? So let someone else answer that. Sammy, what do you think?
If it's a do statement, then you're not going to be storing the value.
Right. Yeah. Yeah, so you might think, oh gosh, I have to know what the return type of that thing I'm calling is. Like, how do I figure out what the return type is of this function that I'm calling? Because it might come from a different file, like I have no idea. So no, you don't actually, because yeah, as Sammy points out, the difference totally is like, is it in a do statement? The only place you're going to call a void function is in a do statement, where you just say do this thing. And the only place where if you have a function that's actually returning something, then it would be part of an expression. Actually, so that's not entirely true. You can have a function that returns a non-void function. You can use it in a do. That's fine. But in that case, you really do want to ignore its return value. So the point is, if you have a do statement, that means you're ignoring the return value, whether it's void or not. It's going to have some return value, and you just throw it away. And if, I guess that actually means you could you could call a void function in the middle of an expression. You could say like output.printint, +3. You shouldn't, and you could imagine a version of the compiler in which that would be an error. If it was doing some kind of type checking, it's like, hey, no, you can't add void and an int. But if you're not doing type checking, I guess it would just generate some code that would happen to take that, whatever fake value it returned, like 0, and it would add it to 3. Don't do that, but. Okay. Any other questions about this? Cool. The other thing I wanted to mention that we didn't quite get to last time, and I just want to mention it quickly. Some of you, may have figured this out just by reading the book or whatever. We didn't talk about at all how to handle parameters. So like, this is another, I think this is another thing from part C, another test case, that's computing the factorial function. So there's 2 functions. Well, that's fine. If you can compile one function, then you can compile 2 functions because you just do it twice. But this function is not void, and it also has a parameter here. So what do you, when you're reading in a function definition, and you read in the name of the function, and then you read some parentheses, and then you start reading if there's some parameters here, what do you need to do with the parameters when you read them in? Anyone have an idea or know what you're supposed to do with these? Simon?
You need to put them in the local symbol table.
Exactly. Not the local. Or you mean, yeah, I know what you mean. The local one. It's not the local segment, but it's the local symbol table, as in those symbols that correspond to just the current function. That's right. Yeah, so there's actually no code that you need to generate for the parameters, but you just need to remember, you say, okay, I have n is an int, and n is an argument, right? So you have this symbol table that is keeping track of, I think we mentioned, like, you kind of have 2 symbol tables. One that's keeping track of local things, that's going to be cleared out every time you finish a function. We haven't talked about the other, like the kind of more global one, because that has to do with class fields and stuff like that. We're going to talk about that later this week. But you just have to remember that I have a variable called n. You have to remember its type, it's an int, and you have to remember kind of what kind of variable it is. In this case, it is a parameter, because the parameters to the function, or the arguments to the function that are passed when it's called, are stored in the argument segment, and local variables are stored in the local segment. So when you see a variable, like here, when you're compiling this expression, you see n, you look it up and you say, n is an argument, so I need to generate some code to, say like push argument 0 or whatever. Right, so the symbol table stores the name of it, the type, what kind of variable it is, local argument, and also the index, right? Every time you see a new one, you like increment some counter. Okay. We'll probably see some more examples of that as we, the thing I'm going to talk about today, but just wanted to mention that. Okay. So today we are going to talk about arrays. And probably we'll just spend all of today talking about arrays. If we get through it, maybe we'll start talking about classes a little bit, but I think we'll just talk about arrays today, and then on Thursday we'll talk about classes and objects and stuff. And that'll take us through the end of the compiler, or that'll be the entire Jack language. So part C was supposed to be due yesterday, and I know there were several people who didn't realize or forgot that it was due. It's okay. I do want you to communicate with me, but if you forget that there was something due and you're like, oh my gosh, I totally forgot this, it's okay. Just let me say, I'm sorry I forgot. Can you extend it? That's okay. But part D will be due Monday, so we'll be talking about that today and Thursday, and then that probably do Monday. And the next week we'll talk about the operating system, which will be due in a couple of installments, kind of the following Monday and Friday, I think. And then, yeah, so this week, arrays and classes. Next week, we'll talk about the operating system. And then the week after that, which is the last week of classes, crazy. My plan is, on the Tuesday, we'll talk about, I just thought it'd be fun to talk about randomness, because on many people's projects, for project 9, a lot of people are like, oh, how do you generate random numbers? And it's like, wait, this doesn't give you random numbers. Like, how does that even work? So I thought it'd be fun to talk about, when you call like random.nextInt in Java, like what happens? Both kind of from a hardware perspective, what kind of things does the hardware provide that can help you generate random numbers? And also kind of from a software perspective, like what is that Java library doing? A lot of interesting things there, and it also depends on what you need the random numbers for. There's different ways you can do it. We can also talk about, maybe we'll go philosophical, like what even is randomness? I don't know. No one really knows, actually, it turns out. And then the Thursday, I think probably, I haven't fully decided, but I think we won't have class and I'll just be available to help work on projects and stuff. So that's kind of the rest of the semester where we're going. All right. So let us look at all right, so this is one of the test files for project 1011D. So this is, let's look at what this does. So it's just a single main function, and it declares an array, A, and then it's got some other local variables, length, I, sum. Prompts you for how many numbers you want. It creates an array. So array.new, that's something that the operating system provides. And it's going to allocate some memory of a certain size for our array. And then it has a loop, and it just loops through all the indices of the array, and it reads, prompts you to type in a number, and it reads it and it stores it in the array, and then it's also adding up all the elements as it goes. If you just want to add up a bunch of numbers, there's no particular reason that you need to store them in an array, but whatever, it's testing our ability to do stuff in arrays. And then it prints out the average. So really the parts that are new, well, just the fact that we have this array variable, and then notice that, right, we can have this, a brackets I thing, and it can happen in two places. It can happen on the left side of an equals, and it can also happen on the right, in an expression on the right side of an equals. And those are very different. I mean, they have some similarities, but they work differently. So we're going to talk about how that's going to work. So I think what I want to do is, let's see. So similar to before, I want to first kind of go through what VM code that we think should be generated for this. I'm not going to write down the VM code for the whole thing, because some of it, we know how that's supposed to work. But specifically the array parts. And then maybe we'll write some pseudocode like we did before for compiling array things. So okay, first of all, when I start reading this function, I'm going to see all these local variable declarations, right? And so I should, our symbol table will have like, A is, a local variable. It has type array, and maybe it has index 0, right? And then, length is going to be local int 1. I is local int 2, and sum is local int 3. Okay. And this is another, let's let's see, actually, does this, maybe it doesn't matter that much. I was gonna say it's very important that we know the types, because we're gonna do something different with arrays. I'm not sure that's entirely true, actually, because we'll know we need to do something different because we'll see the brackets. It'd be more like if we were checking types, we would need to say, oh wait, you can't index, this thing is not an array or something, but. Okay, so we're gonna say, function main has 4 local variables. And then we're gonna generate code code for let, which we know how to do. I'm not gonna write that down. What about let a equals array.new length? Actually, there's nothing different there than what we've done before, because we'll just we'll compile length. So we'll do like we'll say code for let a equal array.new. So we'll say push length is local 1, and then we'll call array.new 1 parameter. And then that's going to return something, and we're just going to say pop, we want to store it in A, so we're going to pop local 0. The fact that it's an array makes no difference, right? Because what is an array actually? Like, what's actually stored in the variable A? Does anyone know what, or what do you think is going to be stored there?
0. The array at index 0.
No. Simon?
Is it just a pointer to the object in memory?
Yeah, and what's a pointer?
A number.
A number, right? A number that means what?
The start of the block of memory.
Right. It's a memory address, right? So the variable A, every variable in Jack is a 16-bit value, right? So A doesn't literally store like an array of values, right? It actually is storing a 16-bit address. That's a memory address that tells us where the elements of the array are stored, right? And this is why we have to do stuff differently with arrays, because if I have an int variable, it literally just stores the int value. And so if I put something in it, take it out, I just literally am copying. But if I have an array variable, it's storing a pointer to somewhere else, and so I have to look that up, go find where that is, do some math to figure out the index, all that kind of stuff. Okay? So this stores the memory address. Well, so array.new, it allocates space for an array, right, on the heap. So it's not on the stack, it's just like some area of memory where we can allocate stuff. Right, and that's something that the operating system is providing for us. So the operating system somehow is keeping track of, there's a bunch of available memory, and when you ask for some, it goes and finds you a suitable chunk and remembers that part is being used now, so no one else will use it, and kind of gives it back to you. You'll do that on Project 12, but for now we can just say somehow there's a way we can get a new array, and it'll just magically give us some memory. Stores the memory address of the allocated array in A. Okay. And then we're gonna code for the while loop. I definitely don't want to write all of that again. I really just want to focus on these 2 lines of code here, because these are the 2 lines of code that are accessing the array. So those are the 2 lines of code that I want to focus on, and see if we can figure out how to generate some VM code that'll do those lines of code. Okay. So let's think about this line first. So what do I have to do in general? Generally, I mean, of course, I have to call keyboard.readInt. I guess we haven't talked about how to generate code for a string. And honestly, off the top of my head, I don't remember how, so I don't want to talk about that. But maybe I mean, it's definitely in your book. And maybe I'll go refresh my memory and maybe talk about it briefly on Thursday. But assuming we know how to do that, though, we have to call keyboard.readInt, and then we'll get back a number on the stack. What else do we have to do? We also have to, we're going to take that value and store it somewhere in memory, but we have to compute the right place to put it. So we're going to have to, look up the value of A. We're also going to have to look up the value of I. And what are we going to do with A and I? Like, how do I combine them, or what do I do with them?
Take the memory address that A holds and add I to it.
Right, I'm going to add them. And this is why array indices start at 0, right? Because the A holds the address of the beginning of the array. And so the very first thing in the array, that's the address where it is. If I added 1, I would be at the next place, right? So since array indices start at 0, we literally can just add the address of the array and then the index, and that tells me where it is. In a real programming language, if you have different, so for example, in Java, when you make an array, let's say you make an array of ints, for example. Well, an int in Java is actually 4 bytes long. And so, when you say A bracket 3, it doesn't have to add 3 to the address. It actually has to add 12, because every thing in the array actually takes 4 bytes. So it has to do a little bit of extra math. It has to look up and see, okay, what type is this array? I have to do a little bit of extra math to figure out, how big each element is, so I can skip the right amount. Right? Jack makes this simple because every single value is just a single 16-bit thing, so we don't have to do that. It's not that hard. It's just like an extra step you have to do. Okay. So then the question is, once we've computed that address, how are we going to, take this value that readInt returned and store it to that address? Right? There's no VM instruction to say, take the top 2 things on the stack and treat one as a memory address and store the other one to that memory address. Right? There's not a VM instruction that does that. So this is where we're going to use that. So if you remember, there's a register called that, and you're like, what is that for? Literally, what is that for? This is what it's for. It's for arrays. That's what we're going to use it for. So essentially, we're going to set that register. We're going to set it to that address where in the array where we want to write. And then we're going to say, pop that 0. Because we have a VM instruction that says we can use the that segment. So basically, we're going to say the that segment is now we're going to change it to point to where we want to write to the array. Now, how do we change the that segment? Well, if you recall, maybe you don't, there's something called pointer. And pointer, actually, I need to draw this out here. Right, so address 0 is the PC, address 1 is, I forget, 3 is this, and 4 is that. 5 is, 5 the temp memory, and I forget.
5 to 12 is 10.
5 to 12 is temp?
I think.
Okay, whatever. I guess 1 and 2 are local and argument, I think, or maybe in the other order, I forget. Okay, but basically pointer is a special segment that always refers to address 3. Just like and temp is a special thing that always refers to address 5. So when you say something like, what we're going to say is something like pop pointer 1. That says take the top value on the stack and store it to the pointer segment at offset 1. Well, the pointer segment is always right here. And so offset 1 is here. If we store something here, it's going to change the value of that. And now, when we do something with that segment, it's going to use whatever address is here. Okay? So this is how we're going to do it. And that's why there's this pointer thing, so that we can change this and that. This we're going to use for objects. Talk about later. I don't know why they're called this and that, as opposed to like this and array or something, but this actually makes sense because this is always a pointer to the current object. It's even like a jack keyword. But that, I don't know why. I think really they just thought it was cute that it was this and that. Honestly, I think that's why. It really would have been better to call it this and array. But oh well. Was there a question?
Maybe it's that because it's like over there.
I mean, this is over there. I don't know.
This, that, and the other.
This, that, yeah. There should be another. Should be another one called, yeah, and temp should be called other. So this, that, and the other. All right. Any questions? So it's kind of, it's very indirect, and it can be a little. At times, it can be hard to wrap your brain around, or you'll probably have to like look at this again, or like go reread and remember how this works. But this is how we're going to do it. So, right, so all that is to say, we're going to look up the value of A, we're going to look up the value of I, we're going to add them, and then we're going to store, that value is an address, we're going to store it to pointer 1, which means it's going to overwrite that. Next, once we've computed keyboard.readIt whatever, then we'll say pop that 0, which is going to take that value and store it to whatever that is pointing to, which is the address we computed. Okay. There's a problem though. So we could literally do what I just said and it wouldn't work. And it's a little subtle to think about why. So what we could do, what we can imagine doing is to say, all right, first I'm going to say, look up, push the value of A on the stack. Then we're going to compile whatever, this might not be a variable, it could be an expression, right? So we'll compile whatever expression is in here, and that's going to, push that on the stack. Then we're going to add, and then we'll say, pop pointer 1. So we'll take whatever we computed here and put it in that. Then we compile whatever's on the right-hand side, and then we pop that 0. Easy peasy, right? Here's why that won't work. What if this part over here has array stuff in it? What if I has array lookups in it? Right? We need to use that for those things also. So we can't figure out A and I, store it in that, and then assume that that is still going to be the same when we actually get around to finishing with this and putting it in that 0. Okay? That's not going to work. There's actually a couple different ways that you can do this. One way, which I think is, there's a way that's I think is nicer, but it requires doing stuff out of order, which means it would only work if you read the whole syntax into like a syntax tree and then go over it later. Which is you actually start by compiling the expression. You compile the expression, it might do stuff with arrays, fine. But then, once it's done, it has its value on the stack, and then everything is done. So it doesn't matter if it changed that. It's done using it, so the value of that doesn't matter anymore. Next, we compile I, and it might also use that and do stuff. But eventually, once it's done, the value of that the value of I, or whatever the index is, will be on top of the stack. Finally, we push the value of A on the stack, add, and then set that, and then pop the value of the expression. But it requires doing things kind of in a right to left order, which is going to be awkward for the way that we've written it. So we're going to do something a little simpler, which is we're going to use temp 0 to temporarily store the address of, what is it? Once we have figured out the address where we're trying to store something in the array, we'll put that in temp 0. And you might worry that the same thing is going to happen, that we need temp 0 multiple times. Turns out that we don't, and I'll see if I can convince you of that. But let's actually write some VM code to do this. So first, we're going to push value of A. So this is going to say push, in this case it's push local, what's A?
0.
It's local 0. Okay, now we're going to compile the index expression, right? Which in this specific case is just push local local 2, right? But it could be something much more complicated because there could be an arbitrary expression inside the brackets. Then we're going to add them. Oops, my hand was shifted. There we go. So we're going to add, this is the base array address. Base address plus index. And now we're going to say pop temp 0. Store memory, target memory address in temp 0. Okay, now we're going to compile the right-hand side expression, which in this case is going to say something like, it's going to compile the string, and then it's going to call keyboard.readInt 1. Now we have the result of doing readInt on the stack, and now we need to get that memory address back out of temp. So we're going to recall memory target memory address. We're going to push temp 0, and then we're going to pop pointer 1. We're going to set that to target memory address. And then finally, we're going to, the result of this, keyboard.readInt is now still in the stack, and we're finally going to say pop that 0. Put right-hand side value into the target. Does this make sense? Any questions about this? So one thing to worry about is, why don't we have the same problem here? How do we know that temp 0 won't get clobbered by something else that happens in between? The answer is that the only time that we're using temp 0 here is when we are doing an assignment statement to an array index. So when I have a let, a brackets I equals something. And you can't have like an assignment statement inside an assignment statement, right? You can have multiple array lookups, but as we'll see, when we're just looking up the value in an array, we're not going to use temp 0. We'll use that. But that's why we had to store this thing in temp 0, so that it wouldn't get clobbered if it was in that. We do have to make sure that we don't use temp 0 any other time when we're compiling expressions. Because if we did use temp 0 for something else while compiling an expression, then that would indeed kill whatever value we had in there, so we have to be careful about that. But we don't have to worry that we're going to do this again while we're in the middle of doing it, because you can't have a let inside of a let. Okay. All right, let's think about this expression, or this thing now. This one it's actually a little bit easier, but it's going to use some similar principles, because the way that we figure out where this value is to look it up is very similar. So, all right, well, we're going to start by compiling the expression on the right-hand side. So we're first going to say, push sum, which is going to say push local, whatever sum is, I don't know, local 3. And now, the value of sum is just going to hang out on the stack, and we're going to do a bunch of other stuff to figure out the value of AI, but it doesn't matter. Like, the value of sum will just sit there on the stack. We're doing stuff above it. When we finally get the value of AI, it'll now be on the stack, and then we can do an add. So eventually, we'll do an add, right? Push value of AI. So how are we going to get the value of AI? Well, first, we can push the value of A. So push local 0. That's the base address. Then we're going to compile the index expression. So in this case, it's just push local 2, compile index expression. Then we add those, because that's the memory address that I want is the base address of A plus the index. And then we need to read the value from that memory location. And the way that I can do that is first I'll put that memory location into that, and then I'll read that. So I say pop pointer 1, which will set that, and then I will push that 0. So read from that, push to stack. Right, so notice I have two adds here. This add is kind of a behind-the-scenes add that's I need to do that addition to figure out the memory location of the array thing. This add is just literally where we compiled this plus operation, right? Okay, and then finally, to finish doing the let, we have to save the result into sum, so we'll say pop local 3. Store result in sum. Okay. So notice, right, we didn't have to use temp at all. We could just do everything with a stack because yeah, it just works that way. So, any questions? One thing that I found curious I was thinking about this just this morning as I was preparing for today. I realized that we only ever say 0 here. Like, we don't ever say, push that 3 or something. And I was like, that's a little strange. Why? Because when I first was reading, I remember when I was reading through the book, and I said, oh, that is going to be used for an array. I kind of assumed that the way you would do it is set that to the base address of the array, and then like if you wanted to write to say, A at index 3, you could say, pop that 3, and it would write to index 3 of the array. The problem is, when you have a VM instruction like a push or pop instruction, you always have to have like a literal number here, right? So what you can't say is, oh, do pop local x, and x is something that I computed previously, right? It has to be like a literal number, and so it's a little difficult if you're doing something like a of I. You can't really. There's no way to say push that I, because that VM instructions don't work that way. Now, so number one, you could imagine VM instructions working that way. You could imagine some other kind of VM instruction that says, oh, we're going to do we're going to do like an indirect push. You just give it the name of a segment, and instead of giving it a literal number, which is the offset, it'll get the offset, it'll like pop from the stack and use that as an offset or something. That would be kind of cool. Or you could imagine, maybe doing some really sophisticated thing where, like, if you notice that you have a loop through an array, you could say, like, oh, I know how long this array is, so I'm just going to, instead of actually generating code for a loop, I'm just going to unroll it and just have, like, I know it's going to be 10, length 10, so I'm just going to generate 10 assignment statements in a row. And I can actually say, just set that one time and then say, pop that 0, pop that 1, pop that 2. Instead of like doing all the addition and stuff every time and like resetting that to something different. So you can imagine using that to make code more efficient in certain special cases. But it's just kind of funny that the way that they have the VM set up, we're only ever going to say that 0. So that will always we'll set it to exactly the place in memory that we want to set, somewhere in the middle of the array, and we'll just like shove something there. But if you recall, like when we talked about the 6502 architecture, right? It actually had some different. Well, that wasn't a VM. That was actually the machine code, but it had some kind of indirect. Some more indirect addressing modes where you could actually, have a register that pointed to the start of an array, and then just say this other register is going to be the offset, and I can just have a loop by just changing that register, and just like, it didn't have to do quite as much work to loop through an array. But. All right, so I think, yeah, I could write some pseudocode, but I kind of feel like, hopefully, by writing this and writing, a bunch of comments interspersed, I hope that will be enough that you could, I tried to say like, oh, this isn't just push local 2. Really what we're doing is compiling the index expression. So when you go to write your actual compiler, you could look at this and be like, oh, right. I'm not just looking up a variable. I'm going to recursively call compile expression on this thing. And then, so. All right, I want to look at, so this one is kind of fun.
Oh, Lord.
So once you get average to work, that one we just looked at, in theory, this test should work also. Like there's nothing that this test requires that the other one doesn't. However, this is kind of more of a stress test. And it's certainly possible to imagine a scenario where you have a subtle bug and it turns out that it happens to work for average, but it definitely doesn't work for this one. Okay? So this is probably going to catch more bugs than this other one. So I'll just let you stare at this for a second and appreciate the insanity. Like, you know, what is this doing? It's like, oh gosh. So we're going to assign to A at what index? Well, to figure out what index, we have to look up something in B, but the index we're going to look up in B is the value stored in A at index 3.
Cancer.
Now before you get too freaked out about this, right? The Jack syntax is recursive. Your compiler is recursive. So in theory, it's actually not a problem. Like if you just say, well, I have a, you know, A bracket something equals something, so I'm going to compile whatever the index expression is, I'm going to compile it. And if that happens to involve an array access, fine, you compile that, and you recursively compile the index of that, and it's just going to work, right? But this is why, like, things like, you know, not overriding temp and stuff become, that's maybe the part of this that's possibly tricky is you have to think about, you know, while I'm in the middle of doing this, what else is going to happen kind of in the meantime, and I need to make sure that doesn't screw up whatever I was in the middle of doing. So let's see. What do I want to say about this? Oh yeah, this is also strange. So you see this? So this is also gonna, right. I think you need this keyword null, which really is just 0. This is a little odd, and like you can't do this in Java. But notice, first it stores, so C is an array of length 1. And then it stores the value null in C0. And then it looks up C0 and stores that in C, which is really just means like we're not storing something in a place in the array, we're actually setting the array variable to null, which means now it doesn't point to that array anymore, it just points to null. So if you ever tried to use C again, it would, it calls print int on C, right? So like, if there's any kind of type checking, this is not going to work. But there's not, so fine. Arrays are just ints, no problem. Simon?
So if the value in C is just 0, then wouldn't the thing in 0 be the stack pointer?
What's the thing in, say that again?
So like if you put 0 in C, then it's like your pointer is now.
Yeah, so if you now wrote to C0, so here, this is gonna, C0 is gonna have the value 0, which is gonna store in the variable C. So C now contains 0. So I think what you're saying is, if you now said like C bracket 0 equals 27, well, C is pointing to 0, and so like, you know, C0 is right there. So that's gonna write the value 27 at memory address 0, which is the stack pointer. Yeah, don't do that. Or maybe do that if you're trying to hack someone's computer, right? So, I mean, but this is exactly how lots of security holes work. Because some languages, like for example C, actually let you do stuff like this. They're just like, oh, you know, yeah, this is an array is really just a pointer, and you can just set it to whatever int you want, and then it literally lets you do exactly this kind of thing. And that can be a problem because you don't want people overriding your stack pointer for some reason. But you cannot do this in Java. So in Java, if you tried to do this, what would happen is that when an array contains null, if you try to access it, it throws an error, right? It's not just 0. It actually is keeping track of the fact that this is supposed to be an array and it's supposed to be null, and if you try to index it, it says, no, you're not allowed to do that. You know, it's a null pointer exception. Now, of course, that means it's doing more work at runtime, because it has to like have some ifs and stuff to test whether something is null. So it's going to be slower. So if you want something to be like literally as fast as possible, then, you know, I mean, it's a trade-off, right? Let's see. Okay, if C is null, it's doing all kinds of more stuff.
Oh, there's more.
C is A3. C1 is 30. Yeah, this is really crazy because it's like assigning numbers from A to the variable C, but then it's looking up like, so it's treating the numbers in A as memory addresses that it's assigning to C, and then like looking up offsets from that. This is truly horrendous code. And you should never ever write code like this, but it should still work. Like, it has a well-defined meaning, and your compiler should generate the proper VM code that you know, will give the right answers.
If we wrote something like that, 150.
Who wrote this? Probably. No, it wasn't. No, this is actually from the.
Oh, okay.
Yeah, it wasn't Dr. Frere. I mean.
I
From
wouldn't put
someone
this.
at MIT.
Yeah, no, it's
Just some schmuck in it.
right. Noam Neeson and Shimon Shaka, the authors of your book. Right? So when I say it's horrendous code, I mean like they fully knowingly wrote this as horrendous code. I'm not saying like, oh, whoever wrote this, what were they thinking? Like, no, they knew exactly what they were thinking. They were thinking they were going to write some horrendous code that abused arrays to make sure that your VM code worked exactly like it's supposed to. Yeah.
Does that mean there's no out of bounds errors?
What is that?
Like index?
Yeah, index out of bounds.
What
Array
is that? I
index.
never heard that.
Array index.
Oh my
I
god.
have no idea what that means.
I don't like that.
No, there's no right. So the only out of bounds error that can happen is if you try to access something
Out
that's
of
like
the
outside of RAM.
Oh my god.
Yeah. Which can happen, right? So you probably encountered this if you were trying to move sprites around on the screen. You like moved it off the edge of the screen, and then it was trying to write to past the end of the screen is like an address that doesn't exist. So yeah, like you can get an error that way. But other than that, no, there's no out of bounds errors.
What would that do in hardware? Trying to write to a RAM address that doesn't exist.
Ooh.
If you sent an address like down a bus, like down an address bus to the memory.
Yeah, I
that
mean,
was-
yeah, so actually, I guess this is a little better than, because this is being simulated, there is actually something that checks and says like, no, that's, you know, you tried to write outside of RAM. In hardware, I mean, it doesn't happen.
it just like does it just like cut off whatever is out of?
Yeah, I don't, you know, honestly, I don't know what real actual hardware does. It's certainly possible that like, it's certainly possible that something at some level, maybe the operating system or maybe even at the level of hardware, kind of is aware of how much RAM you currently have in your system, and if you try to access an address outside of that, it'll throw some kind of, you know, low-level operating system error or something. That's possible. Really, I mean, the answer is much more complicated than that, because real operating systems don't literally, like when you're running a program, you cannot literally refer to a literal physical memory address. Like the operating system says, oh, here is some memory for you. You get these addresses, and you're like, okay. And when you try to access it, the operating system secretly is like, oh, well, actually, this is stored over here. And like, it's translating for you. You know, it's figuring out like, you know, I have my virtual kind of memory that I can access. So I don't know if like but what if like the operating system actually tried to had a bug and tried to access the memory outside of, I don't really know. Probably just, yeah, nothing. It would just, like those wires don't go anywhere, so I don't know. Cool, other questions? What else does this Oh, I see, it's actually making an array of arrays. Cool. So wait, so array.
I still don't like that.
Yeah. Okay, so this code here is not quite as crazy as I thought, because actually A is an array of arrays. Yeah, this is interesting. So one interesting thing, right, is that, like, you know, when we say something is an array, we don't say an array of what? Because it doesn't matter, because all values are the same size. But you don't know. It's like, well, is it an array of ints? Is it an array of arrays? Who knows? But notice this fill function is taking some array A and a size, and it's looping down through the size, and for each thing it's creating an array of size 3 and storing it in the array. So the array A will now contain a bunch of pointers, you know, each to some array of size 3 somewhere else in memory. So then up here, we say, all right, fill A. So A is now going to have 10 pointers in it, each of them pointing to a, you know, an array of size 3. So A is now really a 2D array. It's like a 10 by 3 array, right? So then we say, like, let C equal A3. It's like, okay, A3 is an array. It's a reference. It's a pointer to an array. So C now points to that array. And then when we say C1 equals 33, it's like, go find that array of length 3, set the middle thing to 33, and so on. But yeah, but Jack doesn't. But honestly, like, it makes sense kind of to. It makes a little more sense to us kind of on a semantic level. But Jack doesn't care. If the numbers in A happen to be pointers to other arrays, or if they're just ints, it doesn't matter to it. So there's nothing preventing us from. All right, how much time do we have here? All right. So since we've got a little time left, let's just start talking about classes, and we'll just think through some of what makes it interesting or different, and then Thursday we'll we'll go into much more detail into how things actually get compiled and stuff. So you might recall this square game thing. This was one of the examples that we looked at when we were talking about Project 9. So it's this program that makes a square, and you can like move it around the screen and make it bigger or smaller and something like that. So here's the main class. It just has a single main function. It makes a variable called game, which is a square game. So a square game, of course, is another class, right? So what do you think that the variable game will actually store?
A pointer to an object.
Pointer to an object, right. So same as an array variable. When we create an object, we're going to allocate some memory somewhere, same as we did for arrays. And game, any variable we make that will contain an object is actually going to contain a memory address, which is where that object is stored. So we're calling squaregame.new. Fine, that's going to like allocate the object and fill it in, whatever, and it's going to return us the memory address where it is. Put that in game. Then we get to this. So this is the thing I want to think about. Do game.run. So far, based on what we've seen before, we might generate code for that that would say call game.run 0. Right? Like if, you know, if you had completed your compiler through part C, but you hadn't done part D yet, and you just like ran it on this is probably the code that your compiler would generate. But obviously this is not going to work because there's nothing called game.run. So it would crash and be like, I don't know what game.run is. So the difference, of course, is that when you have a function, like to call this function, this main function, I say, you know, capital M main.main. And that means go call the little m main function that's in the capital M main class. And of course, that'll be, when I compile this class, I'm going to say, you know, function main.main, whatever. And so I can call it, it'll be there. Right, but what is this doing? This is not calling a function, this is calling a method. And the difference between a function and a method is that a method is called on a specific object, right? Whereas a function is just kind of defined by a class generally, and you can just call it kind of on its own. So, what do we actually need to do here? So I'll say you can't just say, so code for do game.run. Can't just say call game.run 0. Nothing named game.run is defined. Right, we're calling a method, not a function. So how does it work when you call a method? Well, of course, in the square, if we look in the squaregame.jack file, there is a method called run. So let's look at that quickly. Squaregame.jack. So here it is, run. It says method void run. That's how we can tell it's a method. And of course, you know, when we compile this, we're going to call it squaregame.run. Because it's the run method that came from the squaregame class. So I guess we actually want to say something like call squaregame.run 0. Okay? But if we did that, how would it know what object we're calling it on? It wouldn't, right? So this is how, well, so think about, if you think about Python, if you've written classes in Python, you remember how there's that annoying self parameter that has to be the first parameter of every single function? Right? What is that? That is the object on which that method is being called. So every time you call a method, the object on which it is called is actually provided as the first parameter. That's how this works. So, so no. Can't just say wouldn't know what object the method is being called on. Okay, really the point is that do game.run is kind of like do square game.run game. And like in Python, it literally is the same thing. Java does this too, but it makes it a little bit more transparent to you because you don't see, there's just this magical variable this that you can use and just like it just kind of shows up from out of nowhere. Really under the hood, this is being passed as the first parameter of a method. Every time you call, you know, if you said like game.run in Java, it's going to pass game as the first argument to run implicitly, but it's like hidden for you. For whatever reason, Python decided to make it more explicit, so you can literally see that there's this self parameter. But, yeah.
I might be remembering it wrong, but calling functions, like from Project 9, when we called functions, did we have to specify the class in the, if we were within one class file, did we still have to specify the class in the call?
Yes.
if you are, I don't recall.
Because we had to do that with the last.
If you're like calling a function or method within the same class,
Yeah,
the question is, do you have to say like,
cause
There's
I
an
was
example
thinking
in,
about how like in
complex
Java you
arrays.
have to.
there's an example in complex arrays?
Yeah. It said main.fill.
Oh, yeah, it says main.fill,
Okay.
right. I think if you're calling a function, maybe you have to say the name of the class, but if you're calling a method, I think you don't. If you're calling a method from another method, maybe. I don't remember, well, I'll I will
it looks
answer
like-
that
it
for
looks
sure on
like
Thursday,
in
yeah.
Square, the
Yeah.
Square example, they did just like do draw, and that's a,
yeah,
like,
okay.
that's a method within the class. But how, like, do we have to process, if we have to do methods and we're like within a class, do we have to process that we're doing, like that's like the class that we're in already, so like
Yep.
the self is implied?
Yep.
Okay.
Yeah, yeah, because at this point, like, if you're in a method of a class, you'll know what this is, what the current object is, and you can kind of pass that on when you call another method. We'll talk about this more on Thursday, and I'll answer that question specifically, but, anyway, so just to finish this, we would basically say, you know, push, you know, local 0, which is, you know, push game, and then we would say call square game dot run 1, because it actually has, it looks like it has no arguments, but it actually has the one special argument. Okay, see you all on Thursday.
That's cool.
Yeah.